Uh, we started recording. We have Emre today in our seminar. He's from University of Iowa and he likes quivers and algebras. So he's going to talk about quivers in algebraic geometry with a lot of examples today. Emre.
Okay, thanks, Özgür. I just want to thank organizers for giving me this chance to speak here. I checked the other abstracts and there is a nice geometry going on here. But I just want to give a more expository talk, also involving some of my results. But I just want to give this a general talk. So basically, I want to talk quivers in algebraic geometry, and we will discuss various examples. And what is the structure? First, I will describe quiver representations. Then we can use these quivers to solve or understand some geometry problems. This is one side. Or there might be equivalences of categories, some quiver side and some geometry side. This is possible. And then another interesting part, we can take notions of algebraic geometry and apply them to quivers. So basically, we generalize things. And why quivers? So let's start with a striking example because this community is more or less interested in geometry. And what would be a kind of a striking result in this manner? Without definitions, so let's do that thing. It turns out that every projective variety is some quiver Grassmannian. So whatever quiver means, whatever quiver Grassmannian means, but somehow this gives us what's generalization, right? Every projective variety is quiver Grassmannian. And for the people who know the story, maybe, okay, this is the form appears in Reinecke. This is just a page-long article, and just abstract says this is the title actually, and abstract says that claim is to prove this result. But historically, these ideas already appeared in works of Ringel, Bailinson, and Lucilla, maybe to name a few. And so this is a tracking point. I will not do quiver Grassmannians today, but somehow we have this generalization. That's why quivers provide a nice setup for us. And so what are my examples I want to talk today? First of all, we can use quivers to understand some geometry problems. And when I say quiver, we will see later that this also comes with these Dinkin diagrams. So somehow we can consider actions of reductive groups or pre-homogeneous vector spaces. And we can use quiver methods to understand their structure, especially to determine which reductive groups act with finitely many orbits. And here pre-homogeneous vector space basically means that it has just only one Zariski dense orbit in the whole space. And one can check the Sato-Kimura classification. And then the second position we can talk is quivers and geometry. So we can talk about categorical equivalences. And first example is the derived category of coherent sheaves on P1 is equivalent to, derived equivalent to the representations of Kronecker quiver. And I will talk that thing at the end. And the other result we can view, we can see the quiver pattern is a category of toric vector bundles. So this is this guy is equivalent to the category of filtered vector spaces, whatever that means. But we can recapture this data of this filtered vector spaces in quiver. We can do that thing. And there are recent papers on the subject. By just using this quiver picture, you try to solve a system of equations, then one can try to calculate this earlier characteristics of these moduli spaces of vector bundles on P2. So, and one nice thing, I guess, for those who have Bilkent background, they will be familiar with this TVVs. Okay. And the other thing we can talk, we have many ideas, many notions in geometry, right? We can apply them to the quivers. If we will discuss exceptional bundles, then we can consider exceptional modules over a quiver representation. There is a notion of stability. One can do that thing in quiver setup, stable representations, or theta stability or Bridgeland stability condition. One can consider quiver Grassmannian for a fixed dimension vector of a quiver. One can consider all possible spaces, right? So though this is just a I just want here I give the structure, and by the way, whenever you have a question, just feel free to ask. Okay. So those are the examples. Basically, I just want to talk, and if time permits, maybe I can mention other things. I add that thing to the last slide, but I'll try to be on time, and I guess I have yeah, I still have enough time. Good. Okay. So I hope it made clear how these quivers appears in geometry. So let's start with definition. So what is a quiver? Quiver is basically a directed graph, okay? And we can allow loops or multiple arrows between edges, okay? So the nodes. So this is possible. And formally, it is just a quadruple, right? We have four pieces of data, Q0, Q1, and S and T. Q0 is just a set of nodes, right? And the points, and Q1 is the arrows between those points, right? We have nodes, we have the arrows, and S and T are just the maps. For each node, we assign a source and the target. So this is just a formal definition. And what is a representation? A representation of a quiver is basically on these nodes, we just put a bunch of vector spaces, right? And we consider also the whole maps between those vector spaces. So this is basically a representation of a quiver. So depending on the graph, this representation type might be wild, right? We cannot detect all the representations, but there are some nice cases. So let's do simple examples. And even let's see in linear algebra setup how we encounter quivers. So this is the Jordan quiver. So we have just one dot and we just map the space to itself. Just imagine that I put there Cn or some vector space V. Basically, this will correspond to endomorphisms of this V, right? And even we can consider the action, conjugation action. Let's send a matrix X to we can consider conjugation action here. So somehow the characteristic polynomial, one can talk about that thing. And that's why it is called Jordan, because the irreducible representations will correspond to this Jordan forms, right? If it is nilpotent. And other example, we can take the A2 type quiver, right? We have just two dots and one map between them. Later, I will do that thing in details, but we can assign two vector spaces, V and W, right? And we consider all linear maps between them. Basically, this is just the home between those two spaces. And then one can define a determinantal variety here, right? With stratified with respect to the rank. We can do that thing. Another interesting example is the Kronecker quiver. And now another linear algebra problem. So let's say we have two vector spaces, V and W, and we have two distinct linear maps, F and G. What would be the indecomposable maps between those two vector spaces? What would be the classification of these maps, right? This is the question. And it turns out that this is not an easy problem. So, and Kronecker considered that thing first. So one need to consider what would be the representations here in the composable ones. And it turns out that one can always use this 1 and lambda. So P1 somehow handles the thing. I will not do that thing in details, but this is an example of the tame representation type. We have a pre-projective component, we have tubular parts, and we have the pre-injective or post-injective parts. Okay, those are just three examples. And depending on the complicated structure of the quiver, one can generalize these things, right? And here A2 just stands for the Dinkin diagram, and we will see in a moment how these are effective. And of course, if we have representations, we want to understand the maps between them, right? Let's consider two representations, M and N, right? For a given quiver, we have a bunch of vector spaces and the maps between them, and we have another guy, right? What would be the representation? And this is basically this diagram should commute. Whenever we have a map in the same quiver for the representation M, and we just want to map the whole thing into this the N representation, and this diagram should commute. So this is the this is how we handle these maps between the representations. And of course, we can compose these maps, right? And therefore, this will form a category, basically. And they will form abelian category. So this is the nice part. So representations, representation Q. Abelian here means that we can consider all the kernels, co-kernels, right? All these things. And of course, we can define a home between this V and W here. Just we consider all these possible things, right? We will need to consider all these homes on the each node. And of course, endomorphism is just map of the representation to itself. Okay. And how we can also keep this data if we, the other idea is the dimension vector, right? Basically, let's imagine that we just consider we have just the enumeration of the nodes, okay? And then for each M is representation, so on each, we have dimensions of these vector spaces, right? We can keep these dimensions on just one array. So this is just the dimension vector. And one nice thing, if we have, let's say, 3 representations, let's say they form an exact sequence, right? M goes into N, maps onto, let's say, P, right? Let's say this is exact sequence, then this dimension vector is additive. So we can add them, right? And just one comment, I will not do that thing, but when I talk about quiver Grassmannian, we just fix a dimension vector and we consider all possible vector spaces that we can put there, right? So this is kind of the generalization. So in the Grassmannian of, let's say, planes, right? In the space, we just consider all possible planes. And here one can consider quiver Grassmannian for a fixed dimension vector. We vary all the spaces. Okay. Okay, and title says that we're gonna do algebraic geometry, but first let's understand representations of these quivers. I just want to focus on the when a representation of a quiver is finite, because there are 3 possibilities. Either representations of finite type, there are finitely many isomorphism classes. It can be tame. For each given dimension vector, there are finitely many non-isomorphic isomorphism classes, right? And it can be a wild, so there are infinitely many vectors. And when this is, we say quiver finite, of course, if it has only finitely many iso classes, right? And this is the old and important result. Basically, a quiver, without relations here, of course, is of finite orbit type if and only if each connected component of its underlying undirected graph, even we can forget the arrows, is a simply laced Dynkin diagram. So this is one important thing. Because the ADE story appears here, right? So and what are those simply laced Dynkin diagrams? We can consider this family AN, right? From the Lie algebra perspective, this will correspond to the SLN, right? Spatial linear Lie algebra, DN for the even orthogonal, and we have 3 exceptions. So E6, E7, and E8, right? So those are just the ADE diagrams, and they appear in various places. And here, as you see, we remove the arrows. It doesn't matter. I mean, independent of the orientation, these quivers gives us finitely many. finitely many orbits. So basically, this is the thing. And again, if you have questions, just warn me. And if I'm going fast or slow, just again, you can say a few words. Okay. I also, I guess I'm co-host. I mean, I see some people are still entering, and some of them have funny names.
No worries.
No, because yeah, it just appears. Those are the moments that I stop. I'm sorry for that thing, because immediately it appears on my screen. Well, it is fine.
Yeah, maybe for the moment I again make you not cancel your cancel that you are
No, it
co-host.
is
so
okay.
that
I
we
mean,
will
just fine.
bother. Okay. Sure.
Let him have fun.
Okay. Now we can also talk about another side, another part of the story. For a given quiver, we can consider the path algebra. And why I'm gonna do that thing, because just to emphasize that we're gonna reach one theorem, not related to geometry, but from its own perspective, which is important. We can consider just path algebra. So we have on each node, we can consider these idempotent functions, the idempotent maps, right? EI square is EI. And if they are belonging to different things, their composition would be 0. We are just considering this concatenation of the maps. And whenever we have a map, we just compose them, right? And composition of these maps with this idempotent guys are simply just, it returns itself. Okay. And why we care path algebras? It turns out that this representation of equivalent to the left modules on this path algebra. This is one when we a difficult, or time to time it might be hard to understand from this quiver representation point of view, which modules appears, what are in the composable modules. And instead of that thing, one can consider the path algebra of the quiver. And then if you know the relations, it is really, really easier to describe the modules, especially the projective modules, injective modules, and simple modules, for example. For projective modules, starting at a vertex, let's say 1, will just be the longest path starting from that vertex, okay? And injective module will be just the longest path coming through this vertex, and simple module will be just representation. We're gonna put k on that node, and the rest will be 0, right? And why these path algebras are important? It turns out that every finite dimensional K algebra is Morita equivalent to some path algebra modulo ideal, right? So we can also form this ideal, right? We can put relations to the paths, and then we can model. So it turns out that this is also, I guess, this should be a result of Gabriel, but I'm not that sure. So that's why quivers are important in algebra, and this is the one reason.
So what does it mean by admissible ideal?
Admissible here stands for, it should be, one can consider a different types of the ideals, right? So we just have this, the radical square, radical cube of these relations, and this is inside of this R2 and R3, the radical square and radical cube, okay? And at the end, in the last part, when I talk about Nakayama algebras, it will be the second interlude, we will see the relations. So basically this will be just ideal, and we just cut out the algebra by these. We just set these some relations to 0. This is basically the idea. Because if we don't allow that thing, and if we have cycles, then this is not anymore, we will have infinite length modules, right? And we don't want that thing in general. Okay. Let's continue. Let's go back to A2 examples. Now I just want to do some geometry, how we can use the quiver information in algebraic geometry. So this is just one example. We can do the following thing. I already told this, but now let's think better. If we have two vector spaces, let's say we attach them on this, let's say here we have V and here we have W, and we consider all possible linear maps, right, between them. And here, by just this quiver, we can attach this determinant to the variety, right? Basically, we can identify this home, because F is an element of home, V to W. We can make this identification with dual of V tensor W, and this can be identified by the matrices. And N and M are just standing for the dimensions of these vector spaces. And we can consider this stratification. We can consider the orbits with respect to this rank. And for example, if this is just square matrices, full rank will be just a generic component. And we can consider the singular locus. So even this linear algebra thing appears here, right? Okay. And here, if we have this matrices X, right, GLV cross GLW acts on this via this change of basis, right, AX B inverse. And of course, ranks are invariant functions. And for matrices, what we know, because of this Gaussian elimination or left and right column operations, we know that there are only finitely many orbits, and those are just ranks. Here, one question arises. So for which representations or for which reductive group actions there are finitely many orbits, how this is related to this quivers, one question. Second, what happens if we add one more arrow here and put two rank conditions, and what kind of objects we are dealing with? And let's do the second one first. What happens if we add one more node? Here we have A3 type quiver, and we can consider the vector spaces V1, V2, V3, and we can consider, so we have maps between them, and we can choose a dimension vector for these R1 and R2, right? As a rank, possible ranks, and one can study its properties. And basically, this is the quiver loci or quiver determinantal loci, and there are many works of the Fulton and also the Buch, right? One can study those. Okay. Now let's talk about these actions of reductive groups with finite domain orbits. This is okay. This is not directly related to the quiver representation, but somehow these quivers encode this Lie algebraic data, right? And I will give this long description, what we're gonna, and this, by using this description, Wimberg and Katz classified these groups acting with, or representations with finite domain orbits for the reductive groups. And then I'll try to combine that thing with one side of my work. So let's see. Here, this is not just simply laced, but let Xn be a Dynkin diagram. It can be any of them, right? You know, there is a B, C, D classes, and then we have E, F, and G, right? And you just pick a node, just distinguish node. And then by using this, we just imagine that we are removing that node, we obtain a grading on this Lie algebra. And basically, by using this grading, it turns out that the representation that occurs in the maximal torus of the G, and it doesn't appear in the connected component. So for details, I just want to refer the Weymans and Kraskevitz paper. They give that thing in a better way. And they consider classifications of E6, F4, and G2 types. And in the old papers of Katz, I guess it is some remarks on the nilpotent orbits. He has this some endless lists. And I guess there were some typos on that thing, but later Katz and Dadok fixed that thing. But also you can find the name theta representations or visible representations and theta groups, sorry, and by the Wimberg. And but more approach and description of the orbits you can find in the Kraskman few of them. I guess one of them is preprint, but anyway. This looks a little bit complicated, but what is the idea? So, okay, sorry. Before the idea, let's make this interlude. Also, let me check my time. Oh, okay. How I am using this data in my research, or how it appeared. So now let's go back more geometric thing, also historical one. So what is a dual variety? So let's start with the projective variety in PN. A dual variety is just basically closure of the set of all tangent planes, tangent hyperplanes to X, right? And we need to take closure, otherwise we will not get the picture. And simplest example, if we have this cubic curve y equals x cubed, then it's dual. You just need to do this trick, just write down the generic line equation, then change the coordinates and do that thing. And what we get this semi-nodal cube, right? And this is just nice thing. And for example, this classical results of Pulcher relating to the dimension, genus, and all these data to the curves can be transferred into the dual variety, right? And there is one nice class of dual varieties called hyperdeterminants. Basically, they are generalizations of these notion of matrix, right? We get multidimensional analogs. And a formal geometric way to do that thing is just we consider Segre embedding of many spaces. Here I skipped the definition, but basically what you do, you consider all products, right? All possible products of the variables, your coordinate functions. And each projective space here is simply just projectivization of C, right? Then excheck the dual variety in this case is a hypersurface, if it is hypersurface. And in general, it is hypersurface. This is the nice part. Then its defining equation is called hyperdeterminant. Okay, so basically those are on this, they live on the tensor. Somehow you can imagine the matrices as V1 tensor V2, but if we add one more tensor, we are dealing with the multidimensional arrays. And if R is 2, if we have just two components, pk1 and pk2, what you get is just the determinant itself, if they are same. And I guess you can find this in many books. This is easy. But what is first non-trivial example? It is just formats, we say 2 and n, right? So you have two matrices, let's say 2 by 2 matrices, and then the discriminant of the determinant of this matrix pencil ax plus by gives you a nice equation. So this is just a very old result, 1848, and they were kind of forgotten for a very long time, but then subject revitalized by Gelfand, Kapronov, Zelevinsky in the 90s. And it turns out that there are so many works on them, just including works of Sturmfeld, Landsberg, and Ottaviani, and it is still active somehow. And we can do the similar thing for the Grassmannian varieties, right? And maybe I can, yeah. We can consider just Pulcher embedding, right? We embed the Grassmannian into this projectivization of wedge K, the exterior algebra. And we can consider the general form, and let's recall the definition of a dual variety. Basically, those are all tangent planes. That's why we can form these forms, right? Here, eta ij's are just the minors of this matrix, right? And this A data will be just the coordinates of the dual projective space. And what we say, this form belongs to the dual variety if and only if it satisfies this vanishing condition. The first order partial derivatives together with the form itself should vanish. So this is the way to describe. In general, writing down these equations is impossible. And maybe one thing here, if we consider just k equals 2, defining equations of these dual Grassmannians will be just Pfaffians, right? Because if the order is even, then determinant is always has always this canonical factor called Pfaffian, and somehow they will give generalization of the Pfaffians in the case of dual Grassmannian. And the last thing, we can cook up things, right? We can consider embeddings of Grassmannian, products of Grassmannian into the space. Here, this notation might be, this is just abuse of notation. And then I can embed this X, which is just tensor product of these exterior representations. We can put them into the ambient space, ambient projective space. And one can consider the local coordinates there, right? And one can consider this generic form. This is a kind of a huge expression. And again, we can play the same game. We don't know the defining equations. It is almost impossible to even write down, even for the known systems. But what we know, we know that F belongs to the dual variety if and only if we have a non-trivial solution, right? And how these things are related to the quivers or the gradings or this methods of Wimberg cuts and Kraskevitz and Weimann. So one can talk about this codimension of singular loci of these varieties, right? We have ambient space. Most of the time, this dual variety is a hypersurface. It is codimension 1. And then that guy has a singular locus. And in the case of hyperdeterminants, the singular locus of the hyperdeterminants, they were classified by Weimann and Zelevinsky. And dual Grassmannian thing classified by Hollweg and Maeda, somehow they studied this problem, but I also include this Jade note. So there are types of the singularities. One can talk about cusp type, which is just basically the quadratic singularities, the determinant of the Hessian matrix vanish. And node means that exactly it is the node. So just imagine that you have one intersection, and on the dual picture, it corresponds to the tangent lines, which are tangent to the variety at 2 planes. And also one can consider further decomposition of that thing. And for the rest of the varieties, the duals of the Segre-Plücker embeddings, this was kind of my result. I don't want to talk about them, but how we can use the quivers in that setup. And in general, again, I'm repeating myself, we have ambient space, we have the hypersurface, and we have, in general, the codimension 2 singularities in the ambient space. But there are exceptions. So this is the list for the generic node component, whatever that means. I just need to, I guess, be a little bit speed up. Except these 10 cases, it is always codimension 1. But what are those 10 cases, or how we how this is related to the quiver? Those are nothing but, if we remember the theorem, if we recall that result, those are nothing but the gradings of D or E types. And we remove a particular node, and then for the remaining variety, what we know, they have finite domain orbits. We don't know the representatives in general, but we know the structure. And for example, let's consider just E6, and let's pick this node. And what happens if I remove this guy? We are just removing that guy, and it attaches to the remaining part, connected part at the 3rd position. So that's why removing that part will give us a grading of wedge 3C6, right? We just need to add one more dimension. So, and the other possibility, here I can remove this node, right? This one. And the remaining part here, this will be just C2. And this guy touches to this connected part at the 2nd guy. So this will give us the representation wedge 2 C5, right? And the other possibility, one can remove this guy. Now this reduces to the hyperdeterminant case, because this is the C2 tensor C3 tensor C3 case, okay? And I just put this wedge 3 C6 and wedge 2 C5 tensor C2. Also, these are pre-homogeneous vector spaces. And what can we say? What is the structure of these exceptions? In the case of Grassmannian, it is normal. Normal means that singular locus is codimension 2 in the hypersurface. If and only if we have these exceptions. So all these exceptions are coming from, one of them comes from E6, the other two comes from E7 and E8. So this is one nice application of the quivers in this setup. Okay. And but this only tells you that the structure of the variety. So it has finitely many orbits, but still, what are the representatives and what are the orbit closures? And of course, what are the ring theoretical properties of those things? Are they complete intersection or Cohen-Macaulay Gorenstein, or spherical varieties? Those are all kind of difficult questions. And you can find lists of this, again, Kraskevitz and Weyman, and based on huge computer calculations. And for example, on this representation, it has 22 orbits. But in the case of Cayley's determinant, it has only 5 orbits. It is kind of, you can write down things by hand, but after some point, it is almost impossible. I hope this gives one side how we can use these quivers in this geometry. And let's pass the equivalences. So now let's talk about this filtration. So this is kind of a nice and important result. So let's, without giving the details, I just want to show how these quiver representations appears here. Also, there are many works on this direction, including Sam Payne and Hille and many other guys. Let's consider a toric variety. So this delta stands for the fun, right? And what is toric vector bundle? So bundle, let's say E, on that thing is torus action on the bundle and the variety, they are compatible, right? And then it turns out that this is, I guess, an early result, 89 or 90 of Klyachko. The category of these toric vector bundles is equivalent to the category of these finite dimensional vector spaces. E, and they have this Z gradings. So we have on the race, we have these decreasing sequences. In general, it might be complicated because this fun might be very, very hard, right? Might be very difficult to calculate. But now that's why let's focus on the P2. On P2, what we just need 3 data, right? Sigma 1, sigma 2, and the third component, because we have just 3 coordinates, let's say X, Y, Z, right? And T acts on them. So therefore we have this 3-armed quiver. Basically, how we can view a rank 2 toric vector bundle, right? So on this intersection point, on this node, of course, here I skip this compatibility conditions, but on this node, we put this C2, right? C2. And for the remaining arms, we just fill the space with C, and at some point, we're gonna get the zeros, right? So this is just the decreasing filtration. So this is the quiver picture of this nice result. And by using this, one can study the earlier characteristic of this moduli of stable bundles, right? And rank 2 is studied by, again, Klyachko, and it is given by this Hurwitz function. I'm just skipping details. And by similar methods in 2011, for rank 3 case is solved, one get more conditions. But the difficulty of the quiver representation also appears here. When we consider rank 4 bundles, here we're gonna have 4, but here we don't know the distribution of these vector spaces in general. And this is a subspace containment problem. And they are in general very difficult, right? I mean, so one need to solve a system of linear equations, and they are not that easy. I mean, just one need to consider all these cuts and the containments. So one can still look to rank 4 or higher rank cases, because the geometric method is easy, because torus, you consider the fixed points of the torus section on the space, and these bundles are just characterized by their discriminant, right? By using the Chern classes. There's no theory is clear there, but the computation part is the difficult. Okay. Okay, let me check my time. I guess I have 20 minutes, Özgür.
Yes, but you can go if you want a little bit longer than that.
Okay, good. Thanks for this thing. And I am sorry if someone needs to leave. Of course, I don't want to steal your time.
What we usually have is a coffee time, coffee break after the talk, and if it goes longer, we can just carry it to the coffee time.
Okay, good. Okay. Thanks for this. Okay. Now let's continue with the other thing, the other premise. If time remains, or maybe in the coffee time, I can talk about the derived category or the result of this Bailinson. But now let's consider how we can take algebraic geometry notions and how we can carry them into the quivers. So this is the other nice part. Whatever we see for any type of vector bundle, one can carry that setup to the homological ideas to the quivers, and then one can study them. And they did a nice mathematics. Now let's talk about exceptional bundles or rigid bundles. And this is a bundle is called exceptional if there is no self-extension. So x1, the higher extensions are 0, and hom is trivial. So it doesn't map onto itself, but hom is just a k or the c, depending on your, so hom is trivial, homomorphism. And a nice, again, old, nice, and known result of Rudakov, basically it gives that ranks of the exceptional bundles over P2 are in one-to-one correspondence with the solutions of the Markov's equation. And one remark about this equation, this can be solved by just a kind of sequence of mutations. If you know a solution, let's say ABC, then the next solution can be obtained as AB and C, AB minus C. So if you know one solution, you can generate all the remaining ones. And those are the Markov numbers. And for example, 111 is solution here, and 112 is solution. And by starting with this 112, you can get this 125, then it goes, right? And somehow, also let me tell, when we consider these bundles, we have this twist, right? We have the twist, and we just consider, Rudakov considers the bundles which has slope smaller or equal than 1/2. He can pull them into this line, and it turns out that these denominators are coming with this solution, this Markov equation. And by this mutation idea, just number theoretic thing, the mutation thing, and it turns out that we have such a mutation on the bundles, right? And indeed, there is a braid group action. So maybe I can show the source. So I hope you see, and this is the nice source. So helices and the vector bundles. And you can see all this Moscow school for the study of these vector bundles, right? Kapronov, Gorodensev, Turin, Rudakov, etc. But what we can do with this? So definition is purely homological, no extension, no non-trivial hom. So we can consider in the composable representation of a quiver, we can say that, okay, this representation is exceptional if hom is trivial, k, and all possible extensions are just 0, right? They don't, modules are not extend each other. And then the sequence, let's say M1 to MR, is called exceptional sequence if every representation, if every pair, we have these conditions. So repeating myself, a module is called exceptional if it is rigid, no extensions, and it has a trivial hom. And then we consider pairs of exceptional modules. They don't have any hom, they don't have any self-extent, they don't have any extension or ext. And it turns out that one can carry this, and this is done by Crowley-Boyevi and later Ringel, and one can consider these exceptional sequences, and then there is a braid group action on them, right? So we just have a purely geometry notion, and we just carry that thing into the quiver setup, and they will lead a nice mathematics again. And later at the end, I can mention why this exceptional collection appears in the algebraic geometry, because somehow they generate the derived categories. So then they will deserve a special name. They will be strong exceptional collections. Okay. But now this is but when we carry things into the quiver setup, we face another nice problem. So let's consider just this finite representation type, finite representation types. And there are finitely many modules, therefore there are finitely many exceptional sequences. And then what are the numbers? So for a given quiver, or how we count them? Is there a nice combinatorics going on there? Because even from this part, they solve this Markov equations, right? This is what we expect. We expect a high combinatorics there. It turns out that in the case of AN, just this, if you remember this equi-oriented quiver, right? The AN type, and the numbers are n plus 1 to the n minus 1. And one nice thing, this is simply the number of all parking functions, or the all forests of labeled forest of length at most n, right? And this is one nice result. And people later studied their combinatorial models. For example, you can find the works of Ralph Schiffler and Igusa, and there are many results. And also one can consider the derived category. Here just, okay, let me check. Yeah. Here one nice comment: if algebra is hereditary, equivalently quiver is acyclic, and global dimension is just 1, right? We don't have long resolutions. And then it is kind of easy to describe the derived category of this type AN. We just consider the shifts by 1, right? Because it is triangulated. And in the case of this derived category, the number of exceptional sequences is equivalent to the number of spanning trees. So this is a result of RAI, I guess it's about 2012. So they are combinatorial objects. And now I just want to talk the second interlude, what I did, not big result, but it is kind of a nice small thing. Now let's consider this radical square zero Nakayama algebra of rank n. And I remember there were one question about this admissible ideal. I didn't write the ideal picture, but basically we only have length at most 2 modules, right? This 1, 2 stands for the projective module. Basically, it means that on this 1 and 2 nodes, we have KK and the rest is 0, right? This is just one representation. And the radical square 0, so we don't have any length 3 module, right? And it has a very nice outstanding writing quiver. It is kind of easy. And these guys are the simple modules. We have simple modules on each node, right, vertex. And we can index them by these numbers. And we have the projective modules. And of course, this guy is injective, simple injective, and this is simple projective module, right? And one can form the projective resolution. One nice thing about this generalization of this notion of exceptional sequences into the quivers, if algebra is not hereditary, one need to consider all possible extensions, right? So this algebra is kind of interesting because its global dimension is n-1, because resolution stops at this simple at n, projective. And we can describe these homes of these modules by just combinatorial. For example, 2 consecutive projectives have the map between them, but not we cannot jump, right? And also projective modules here cannot extend each other, right? Only, for example, 1 and 2 can extend, and they give the projective module. And now I want to count the exceptional collections here. So what is the collection? It is a nice small result. The enumeration, the following are equivalent. So enumeration of this complete exceptional sequences means that there are n modules in my collection. Sequences of linear radical square 0 Nakayama algebras. This is equivalent to the enumeration of idempotent functions. And also it is equivalent to the enumeration of the forests of rooted labeled trees of height at most 1. The items 2 and 3 are known to be equivalent since 1960s, I guess, but the number of exceptional sequences for a given algebra appears here, and somehow it is nicely combinatorial thing. And this is the result. And one can still ask, for finite representation type, what are the exceptional collections? And in general, it is not easy. So if you have a nice patterns or combinatorial things, then one can generalize the objects. And now let's talk about the last thing, because okay, I just want to finish in 8 minutes. I just want to obey the general rule. What would be the other example? Just I want to briefly mention. The other thing is the following. So one can consider this derived category of coherent sheaves on P1. And basically, it turns out that this is equivalent to the representations of the Kronecker quiver. So the quiver we just briefly mentioned. And how one can do that thing? Basically, it turns out that the derived category of this P1 is generated by this O, the structure sheaf, and O1, right? And in the derived category, generator means that one can consider all the shifts, and also we have the mapping cones between them, right? And nicely, it fits to this Kronecker quiver representation. So this is kind of an old result, I guess, 1978. Coherent sheaves on P and problems of linear algebra, I guess. And one other thing, I mean, if you see some old text article which says problems of linear algebra, basically they are referring to this type of stuff, so quiver representation. So this is the one nice thing. And also one can generalize that thing to Pn, right? This will be just vast generalization of the Kronecker quiver. We will have the n+1 nodes, and for each of them we have n maps, and then we will put some relations. In general, it is very difficult to write down the relations because the relations will come. But how we do that thing, we consider just endomorphism of this tilting module or bundle. Maybe I can say a few words on that thing. And nice thing, those invertible sheaves are just form an exceptional collection. So this is just they don't have any self-extension, they don't have any map between them, right? That's why no map for one direction. So this is a nice exceptional collection, and it generates the derived category. And one thing, what we say about these tilting bundles, also it appears nowadays in the context of this cluster theory. Those are the bundles, the modules of projective dimension at most one, and don't have self-extension, and they appear in their resolution. So the A appears in as a kernel of the map, right? And one can use the tilting bundle. One can define that thing, and so this is another example how we have two sides of one thing, right? Geometry side, it is the coherent sheaf, right? On quiver side, it is just a particular representation. So also there are works of Bondal and Kapronov on the subject, so you can check the references. And I didn't put I know I was sloppy about the references, but those are kind of a very well-known examples. When you just Google it, things will come immediately, right? I mean, we are not living in the 90s. Maybe last words, closing things. What are the other possibilities? I mean, those are not just limited to these things. I choose these quivers because somehow it reflects, or I'm using them in my research. But what are the other things? Just few words. One can consider this quiver moduli, right? The basically Nakajima quiver varieties. We have the notion of stability, stable bundle, right? If you brief the definition, one can define the slope there, the degree of Chern class over the rank, right? And a bundle is called stable if every sub-bundle satisfies some numerical condition. One can carry that thing to the quiver representation setup and study this quiver moduli, right? And of course, one can consider this semi-invariance of quivers. If we recall the A2 example, we have this home acting on the each representative V, right? Each vector space. They will what is the ring of invariant functions on those the objects, and it is a Schofield's Skowronski's and Weymann's result. It turns out that they satisfy nice properties like complete intersection if and only if the underlying quiver is either a Dynkin quiver or a fine Dynkin quiver. We add just a few more nodes, right? And of course, there was a proof of this famous saturation conjecture by just using quivers. It is given by Derksen and Weymann, but for the more history, one can check results of Fulton, Alan Knudson and Terence Tao, right? And again, few things about, we can say, result of Klyachko. He showed the weak version of that thing, right? Those are the other things that touch to the geometry. I mean, they are directly related to the quiver. And in general, whenever we have a geometric notion, one can carry that thing into the quiver setup. But with this difficulty, in general, the representations of quivers are wild. We don't have too much control. Things are getting harder and harder. But if one can do something there, then this is always remarkable. Even just working on the Dynkin diagrams is kind of, they are not always easy, right? For example, we didn't talk about this DN quiver loci. There are just recent works, the Ryan Kinser and Jenna Rajkov. So those are all open fields. So the bunch of questions, so many questions, and I believe they produce a nice mathematics. So I just want to thank you for listening to me. Yes, and I was on time. Okay.
Yes, thank you.